This is the first video for the Chapter 3 notes. Chapter 3 is describing, exploring, and comparing data. 3.1 is measures of center. Measures of center is a value in the center of the middle of the data. This is either going to be the mean, median, or mode, and we'll talk about each of these down below in just a moment. So the first one that we're going to discuss is going to be the mean, or arithmetic mean. And this is the measure of center found by adding up all the observations of data and then dividing by the number of observations that we have. And we have both the population mean and the sample mean. And the big thing to note here is that they're both calculated the same. However, the notation for each of these is going to be different. And so for population mean, we use the symbol mu. This is a Greek letter, and this is used for the population mean. Remember, the population is all elements that we have within a set. And then we have our sample mean, which is that subset. And for that subset, we're going to use X bar. And so X bar is for our sample. And the symbol sigma tells us to add up all the numbers, and you can see that up above. The nice thing with this course is going to be that we are not going to be calculating anything by hand, so everything's going to be using a calculator. And so down here you'll notice that there is a box, and that box is going to be the steps that we need, and it will tell you which type of calculator this is for. And so it says steps for finding the mean and the median using a TI-83 or 84 graphing calculator. And on here, the first thing you'll notice is that stat has a box wrapped around it. That means that that's a button that is on your calculator. And so it says to go to stat, go to edit, it should be on there by default, and hit enter. And you're going to input your data into L1. Then you're going to hit your stat button again, go to calc. This is going to require you to scroll right and go to one of our stats and then press enter twice. It will give you a bunch of output, but the two that we're going to be discussing right now is going to be X bar, this is the mean, and then MED, this is the median. The calculator does not use mu, so your job is to understand if the data set is from the population or from the sample. Right above that, it talks about resistance, which is a statistic. Is resistant if the presence of an extreme value or an outlier, which we'll talk about later this chapter also, does not cause it to change very much. An important properties about the mean is just one extreme value can change the value of the mean drastically. And so we have next topic is median. And median is going to be denoted with a capital M. Again, the calculator writes MED for median, but for us we'll be using a capital M. Of the value is going to be the measure of the center, so that's the center of our variable, and that is the value that lies in the middle of the data when the data is arranged in order. So important properties about the median: an extreme value does not change the median by a lot or at all. So we have an example here that says find the mean and the median of the exam scores of the 15 students in an algebra course. The scores are, and they are given to us right below. And so in order to do this, we do need to use our graphing calculator. We are going to be using the graphing calculator for every single chapter, starting in chapter 3. So it's important to make sure that you either have the graphing calculator or have the app to be able to use. To use the graphing calculator, I'm going to demonstrate this on an app. And remember that all graphing calculators are a little bit different. So any questions, make sure you stop by during office hours to discuss your specific calculator that you're using. So on our graphing calculator, we are going to go to Stat, Edit, and then in L1, we need to enter in all of those numbers. Once you have them entered in, you need to go back and double check to make sure they're entered in correctly. If you enter in the first number, you can select enter to get to the next or use your down arrow button. From here, you need to select stat again. We're going to go to calc and then one of our stats. From here, you can either type in L1 or just select enter. If you have the physical graphing calculator, it does ask for you to type in L1 for your list. Select enter, and you'll notice you get your results on the screen. From the calculator, we get that X bar, since this is a sample, is going to be 79.07, rounding 2 decimal places, and M, which is our median, is going to be 80. The example right below says to find the median of the miles traveled to work, and there is a list of numbers there that we need to put into our L1 on our calculator. On your graphing calculator, you need to go to Stat, and then Edit, and then enter all of your numbers into L1. Again, double checking to make sure they're in correctly. Then select Stat again, your Stat button, go to Calc at the top, go 1 var stats, select enter, and you'll notice you get your results. From the calculator, we get the median, or just M, is equal to 12. And you can go ahead and put units with this for miles, which is what we're discussing. On the next page, it says the data below represents the miles traveled to work by 10 employees at a local ice cream shop. And we just saw those same numbers in the previous example. It says compute the population mean. And so if you go back and you look at what you were given on your calculator from this, and we're using for population will be mu, and this is going to be 13.4 miles. Part B says to find a sample. This is going to be a simple random sample of size n equals 4 employees, so we'd randomly select 4. For simplicity and to making sure that we all have the same 4 people that are traveling to work, I randomly selected them. So I selected 8 miles, 12 miles, 18 miles, and 5 miles. So this is going to be our sample. And so we need to put these 4 numbers only into our calculator and going ahead and calculating the mean using our graphing calculator. On your graphing calculator, you need to go to Stat, Edit, and enter in all your values into L1. This only has 4 numbers that you need to enter, but double check to make sure they're entered in correctly. Next, your Stat button again. Scroll right to Calc, go to 1 var stats, and select enter, and you'll get your results. And for our sample mean, we use the notation X bar, and our sample mean from the calculator is 10.75 miles. Part D says to create a frequency distribution, and it asks where is the population mean. So if you go ahead and look at how many people drove 0 to 5, you'll notice there's only 1 person. Going 6 to 10 miles, there are 2 people. 11 to 15, there are 4. 16 to 20, there are 2. And then people that are driving 21 to 25 miles is just 1. And again, this is using the idea that we had from last chapter in chapter 2. And it asks for where is the population mean. So our population mean is up here. It's 13.4, and if you notice, 13.4 is going to be here, somewhere in that middle. So it's in the middle. And right below it says the population mean is in the middle of the distribution or middle of a histogram or distribution. So it could also be in the middle of a histogram. The example right below this says the data below represents the lengths in minutes of Jason's cell phone calls on the day. Find the mean and the median of the data and determine which measure of center tendency that you think better describes the typical call length. On your graphing calculator, you need to go to Stat, Edit, and enter in all the values into L1, double checking that they're entered in correctly. From here, you need to select Stat button again, scroll right to Calc, select one var stats, and select Enter. From here, you'll see your mean and your median. So the central tendencies that we have right now are either going to be our mean or median. And if you look at the cell phone calls, you'll notice that most of them are relatively short, except for that last phone call of the day, which was 52 minutes. There's a dot plot given down below, and this is going to be lengths of calls in minutes, labeling our axes here. And so the mean for the data, in order to calculate this and along with the median, we need to take our numbers and input them into L1. From the graphing calculator, we get that the mean for our sample is going to be 8.3 minutes, and likewise that median is going to be 3.5 minutes. And you'll notice that those numbers are pretty different, so the mean and the median are not very close to one another. And the reason why is because that 52-minute phone call is really extreme compared to all the other numbers. And so right below this, it says the median better demonstrates the typical call length. The 52-minute phone call is an extreme observation and causes the mean to increase substantially and has no effect on the median. And so it says, for example, if the 52-minute phone call was changed to 8 minutes, then our calculations would be x bar is 3.9 and m is equal to 3.5. So the mean changed and the median did not. Similarly, if the 52-minute phone call was 152 minutes instead, then x bar is going to be 18.3, and our median doesn't change either. It stays at 3.5. And so that mean drastically is changed based upon that value that we would have for all of our numbers, whereas the median did not change. The next thing we have is mode. And mode is the most frequent observation of the data set. This can be either quantitative or qualitative, so we can actually deal with categories in this one. So we also have two interesting scenarios that could arise. One's going to be no mode or multiple modes. So no mode is going to be no data value is repeated. So an example of this would be if we had 1, 7, 3, 16. You notice each of those values only occurs once and nothing occurs more than any others. Or we could have multiple modes. This is going to be multiple data values repeat the same number of times. So for this, we would have an example of maybe 4, 2, 4, 7, and 2. And you'll notice that 4 occurs twice and 2 occurs twice. So they both occur the same amount of times. So 2 and 4 would both be our modes. Important properties about the mode. You can find the mode of qualitative data. So again, that categorical data. So the example right below says, find the mode of the data set above regarding miles driven to work. And the miles are listed there again. And so the mode is going to be the one that occurs the most. You do not need to use a graphing calculator to do this at all. You just need to look at the numbers and realize that 12 is our mode since it occurs the most. Which is twice. The next example at the top of the next page says the table below lists the color of cars driven by 12 college students to determine the mode color of the car. And so taking a second to look at this, you'll notice that we have a total of 3 black cars, and we also have a total of 3 white cars. So black and white are both our modes, and this is because they both occur three times each, which is more than any other color. The next thing that we have is called mid-range. And mid-range of a data set is the measure of center, that is the value midway between the minimum and the maximum values of the original data set. And so the little formula is given to you guys down here. you would have to take your max value and your min value, add them together, and divide by 2. Important properties about the mid-range is that they're very sensitive to extreme values. So our example says to find the mid-range of Verizon data speeds. They are listed there, and these are all in megabits per second. And so you need to find your largest value and your smallest value. So our largest value and our smallest value, and add those together. So our mid-range is going to be our largest value, which is 55.6, plus our smallest value, which is 14.1, and divide that by 2. So adding those numbers first, getting that sum, and then dividing by 2, you should get 34.85. And then again, this is in megabits per second. Grouped data. So sometimes we're dealing with group data like we did in chapter 2. And group data is when data is summarized in frequency distributions or tables. We cannot find exact values of the mean or the standard deviation, which are discussed in a moment, but we can approximate these measures. And so there's some formulas down there, but again, we are going to be using our graphing calculator. And so steps for finding the mean standard deviation for a group frequency distribution with the TI 83 and 84 graphing calculator. So again, we're going to go to our stat button, go to edit, and the difference here is going to be we're going to actually input numbers into L1 and L2. So L1 is going to either be the class midpoints or the exact values if no range is given. And then for L2, we're going to either put in our frequencies or our relative frequencies. Then we're going to hit Stat button again, go to Calc, one of our stats like we did previously, hit Enter, and you'll notice that it's going to ask for some information to be listed. And so this is what you would have to enter in. So if you put your numbers, your midpoints or your data values in L1, then you type L1, and your frequency list that you put in we'll put into L2. So you make sure you tell the calculator where to look and find those values. Go to calculate and select enter, and then you're going to get your approximate values. And you'll see that the first one is approximate sample mean, the second one is approximate sample standard deviation, and the third one is the approximate population standard deviation. And so with this, we'll talk about standard deviation shortly. And so we have an example here. You'll notice that this is grouped data since we have a range of values and corresponding frequencies with them. And so in order to do this problem, we will need to calculate midpoints. So the example says, following data represents SAT mathematical scores for 2024. Find the approximate mean of the data. So in order to do this, we first need to calculate our midpoints. Remember, in order to calculate your midpoints, you add together the lower bound and upper bound, get an answer, divide by 2. So 200 plus 299, divide that by 2, you get 249.5. For class 2, 300 plus 399, and then divide that by 2, you get 349.5. And then going ahead and calculating the rest of these, you get 449.5, 549.5, 649.5, and 749.5. So on your graphing calculator, you need to enter in your midpoints and your frequencies. And so your midpoints are going to go into L1, and your frequencies are going to go into L2. On your graphing calculator, you need to go to Stat, Edit, and enter in your midpoints into L1 and the corresponding frequencies into L2. Again, double checking to make sure your numbers were entered correctly. Next, we go to Stat, Calc, one var stats, and because you put numbers in both L1 and L2, you need to tell your calculator to look there. So I'm going to select second 1, comma, second 2. So it should say L1 and L2. Again, if you have a calculator that is a physical calculator, it is laid out a little bit different. And your list is going to be L1 and your frequency list is going to be L2 as stated on the bottom of page 3 notes. From here, select enter and we arrive at our values. From the calculator, we get our approximate mean, which we're going to use mu since this represents all of our SAT mathematical scores for 2024, and we get 519.74. Right below it says the weighted mean, and this is denoted X bar, is an average in which each quantity to be averaged is assigned a different weight, W. These weightings determine the relative importance of each quantity on average. In other words, a mean where some values contribute more than others. There's a formula down here that we're going to use to compute this, and this is like your grades. So you might be taking a class that's 5 units, and you might be taking a different class that is only 3 units. So obviously that 5-unit class is going to weight more than a 3-unit class. And so we're going to sum up all the weights times X, which is the value of the ith observation, and W is the weight of the ith observation, and then divide by the sum of all the weights. So we have an example right below that says Jason just finished the fall semester and earned an A in his 4-unit trig class, a B in his 3-unit business class, a C in his 3-unit English class, and a B in his 5-unit biology class. Determine Jason's grade point average. We first assign point values to each grade. Let an A equal 4 points, a B equal 3, a C is 2, a D is 1, and an F doesn't count for anything, so it's 0 points. And so to calculate our GPA, or X bar, we're going to sum up the weights times that value, and then divide by the sum of all the weights. So looking at the numerator, the first class that he took, he got an A in, and it was 4 units. And an A is 4, and it's a 4-unit class, plus the next course that we have is a B in a 3-unit class. So that's 3 units, and a B is worth 3 points. Plus, and then the next one that we have, he earned a C in his 3-unit English class. And so 3 units and a C is worth 2 points. And then his last course that he earned was a B in a 5-unit bio class. So 5 units and a B is worth 3 points. Now we're going to sum up all of those weights. So total units, so 4 plus 3 plus 3 plus 5. And working this out, we get 46 over 15, which you can divide on your calculator. I'm going to go ahead and round 3 decimal points, and we get 3.067. And so this is the GPA that he earned for that semester. The next section that we have is section 3.2, measures of variation. Measures of variation are used to quantify the spread of data. Numerical measures for describing the dispersion or spread of data in this section are going to be range, standard deviation, and variance. So this is the dispersion or spread of our data, and the large one that we're going to be using is going to be standard deviation. So the first one that we're going to discuss is range. It's denoted R. Of a variable is the difference between the largest data value and the smallest data value. And remember, difference means subtraction. There is a little formula given, so largest data value minus smallest data value. Important property about the range is it's very sensitive to extreme values. So from the example above, we have all the miles that are traveled to work, and it wants us to compute the range. So the largest data value, if you look at your list, is going to be 23 miles. And the smallest data value that we have is 5 miles. Therefore, our range is going to subtract our largest minus our smallest, and we get 18 miles. Next thing that we have is standard deviation. This is the most important one that we have for our chapter. And so standard deviation is a statistic that tells you how close the various data points are clustered around the mean. So there's 2 bullet points right there. First one says if the data point sets vary greatly from the mean, this means that they are more dispersed or farther from the mean, then the standard deviation will be large. If the data points in the set varied only slightly from the mean, or they're more clustered around that mean, then the standard deviation will be small. So there is a graph down below with our clustered, or our data points that are close to the mean, and it has a smaller standard deviation, or where it's more dispersed, like that second graph, and it's more spread out, and so we have a larger standard deviation. We have our population and sample standard deviation notation down below. So population standard deviation, we use sigma. This is a Greek letter and it's called sigma. It looks almost like a P that fell over. And this is measure of how much data the values deviate away from the population mean. The sample standard deviation is denoted with an S. And so for this, it's the same thing but dealing with the sample mean. We have 2 different formulas to calculate standard deviation of a sample. The formulas are similar for a population except for dividing by n instead of n-1. We will not be calculating the standard deviation by hand, so this course you should not be calculating this by hand. Instead, we'll be computing it using our graphing calculator. So the next thing that we have says important properties about standard deviation. It's not negative. Large values indicate greater variation, and units are the same as the original data. So there's an example right below that says the following frequency distribution represents the number of live births in thousands in the U.S. in 2024 by the age of the mother. Determine the population mean and the standard deviation for this data set. So we're asked about the population mean and standard deviation. And so for this, we have the grouped data. You can see that first group is 10 to 14. And so because we are dealing with group data, we need to calculate those midpoints first. Remember, that's adding the lower class limit, upper class limit, and dividing by 2. So 10 plus 14 is 24. Divided by 2 is going to be 12. Calculating the rest of the midpoints for these classes, we get 17, 22, 27, 32, 37, and 42. So in order to do the calculations, we had the steps earlier in the notes, but we do need to put our numbers in. Our midpoints are going to go into L1, and our frequencies go into L2. And so we need to use our graphing calculator and input these values in. On your graphing calculator, you need to go to Stat, Edit, and enter in your values into L1 and to L2. L1 needs to be your midpoints, and L2 needs to be the births that are listed in thousands. Again, double checking your numbers. Then select Stat, go right to Calc, and select one var stats. And because you put numbers into both L1 and L2, you need to tell the calculator to look there. So we're going to go second 1, comma, second 2, close your parentheses. Again, if you are using a physical calculator, it does ask for the list, which is L1, frequency list, which is L2. Select enter, and we're going to round our answers 2 decimal places. From the graphing calculator, we get a mean. I'm going to use mu since this is a population mean of 27.37 years. And then on our calculator again, you need to make sure you look at the sigma one since we are dealing with a population standard deviation. And for this value, we got 6.28 years. Right below it says the range rule of thumb for identifying significant values. And it also goes on to the next page. So significantly low values are going to be values that are mu minus 2 sigma or lower. Significantly high values are going to be mu plus 2 sigma or higher. And values that are not significant are going to be between those two expressions that we have, which is going to be mu minus 2 sigma and mu plus 2 sigma. So on our graph up above, the mean is going to go in the middle. So I'm going to go in and put mu. And I'm going to go one standard deviation each way. And then I'm going to go a second standard deviation each way. So I have mu plus 2 standard deviations and mu minus 2 standard deviations. And anything that is not significant is going to be between these two values, and then significantly high is larger than mu plus 2 sigma, and significantly low is going to be mu minus 2 sigma. Right below this, it says variance of a set of values is a measure of variation equal to the square of the standard deviation. The population variance is sigma squared, and the sample variance is s squared. Important properties about variance. Units are square units of original data, so not really making any sense. We do not use variance as much in this course, but it is used in a lot of other calculations. Right below this, we have what's called our empirical rule. Give that a star. And it says that it is, if a distribution is roughly bell-shaped, then we have some values here with percents. So approximately 68% of the data will lie within one standard deviation. And you can see that 68 down here below. And then it says approximately 95% of the data will lie within 2 standard deviations. And again, you can see that 95 below. And approximately 99.7% will lie within 3 standard deviations. And so you can see the percentages. 68%, if you split that in half, is 34 on each of those, and so forth with those percents. And it says the empirical rule is the same based on sample data, with x bar used instead of mu and s replacing sigma. Section 3.3 is on measures of relative standing and box plots. So the first thing that we have is what's called a z-score. And a z-score, or a standard score, or a standardized value, is found in converting a value to a standardized scale. This is the number of standard deviations that a given value x is above or below the mean. So the population z-score is going to be the data value x minus the mean divided by the standard deviation. And you'll notice it's going to be the same for also the sample, except instead the notation is going to be x bar and s representing your mean and your standard deviation. Important properties of our z-score is going to be that the z-score is unitless, and it has a mean of 0 and a standard deviation of 1. And this is really key in understanding z-scores. If the data value is larger than the mean, then the z-score is going to be positive. Again, remember the mean is 0, so that would mean those values are positive. If the data value is smaller than the mean, then the z-score is negative, since it is on the left of 0, and it would be negative. A data value is significantly low if the z-score is less than -2, and a data value is significantly high if the z-score is greater than or equal to +2. The reason why -2 and +2 is because our standard deviation is 1, and as stated up above on the top of this page, you'll see that significantly low are going to be the mean minus 2 standard deviations, so 0 minus 2 times 1, which would be -2, and significantly high values are going to be mean plus 2 standard deviations, or 0 plus 2 times 1, which works out to being 2. Right below this, it says the z-score provides a way to compare apples and oranges, different data sets, by converting values to the same mean and the same standard deviation when they actually have different means and different standard deviations. Remember, the mean is going to be equal to 0, and our standard deviation is going to be equal to 1. So there's an example right below. that says a student takes 2 exams, getting 55 on test A and 60 on test B. The class scores for each exam are normally distributed or bell-shaped. For test A, the mean is 50 and the standard deviation is 5. For test B, the mean is 50 and the standard deviation is 12. Find the z-score of the 2 data sets and compare them. So z-score for test A, the formula was given at the bottom of the previous page. And so it's going to be the value that you had that you earned on test A, which was a 55, minus the mean, which was 50, and divided by the standard deviation, which is 5. Working this out, you get 5 over 5, which just simplifies to 1. For test B, to calculate our z-score, we earned a 60 on test B minus the mean for test B. So if you read above, the mean for test B was also 50, but we're going to divide by the standard deviation for test B, which is 12. This is going to simplify to 10 over 12, which is 0.833. So the z-score for test A is 1, and the z-score for test B is 0.833. So now we can look at these since test A was scored out of a different amount of points with a different standard deviation than test A and B. And so we now have a mean of 0 and a standard deviation of 1 with z-scores, since these are both converted to z. And so if you notice, your z-score is larger for test A than it is for test B. So this means you did relatively better on test A than you did on test B. So the z-score for test A is larger than the z-score for test B, and this means you did relatively better on test A. We can use z-scores to identify significant values. So again, the mean is 0, going 1 standard deviation each way. I'm going to have -1 and +1 since our standard deviation is only 1. Going 1 more standard deviation, I get +2 and -2. And so values are not significant if they're between -2 and +2. They are significantly low if they are less than -2 and significantly high if they are greater than +2. The example right below says the weights of kittens is roughly bell-shaped or normally distributed, with a mean equal to 3.6 pounds and a standard deviation equal to 0.4 pounds. The weight of Maria's cat is 2.7 pounds. Is this value significantly low? So in order to figure this out, we're going to calculate our z-value. And the z-value is going to be our weight for our cats, for Maria's cat, minus the mean, divided by the standard deviation. And so for this, we know that Maria's cat weighs 2.7 pounds, minus the mean, which is going to be for 3.6 pounds, divided by the standard deviation, which is 0.4. So subtracting those values and then dividing by 0.4, we get -2.25. And so this is our z-score of -2.25. And is it significantly low is what we're asking about. And so up above is significantly low, and it says a z-score value of -2 or less. And so -2.25 is smaller than -2. So yes, this is significantly low. And the reason why is because -2.25 is less than -2. So this concludes our first video for chapter 3. So make sure to watch the second video for chapter 3 to complete all of your notes.